same kind of way. Like,
Yes.
Not in like a perverted way to say, oh, he's just weird.
It's not like real cool like Fisher.
No, Fish is amazing. Are you kidding me?
What?
Fish is amazing.
I didn't say he wasn't.
I
I was agreeing with you.
Yeah, he's awesome. He's hilarious because he roasts people that when they're not paying attention. And he told on Grant Economics, like, Grant, you're listening, aren't you?
Oh, you're not listening much or what?
I don't know really why.
He thinks Grant doesn't listen, even though he does. I mean, I don't know. That's weird. I'll look forward to it.
Aren't you going into business or something?
Yeah.
So, you could keep the book open and follow if you want. We're not going to like read a bunch of this, but there are some pictures that could be of use that I might refer to. Chapter 18. Okay. So what we're going to be talking about in this section is the potential difference that you get when you use a galvanic cell. Galvanic cell. I can't remember already.
It's galvanic.
Galvanic, okay.
I'm just picking one. I don't know either. Volcanic.
How we've done a bell ringer all year.
We don't have time for bell ringers in this class. We go through like 15 minutes of homework usually every day.
Yeah.
But depending on the day. I mean, if it's the electron configuration, it's like 35 minutes, right? For that day.
Yeah.
Yeah.
You can play about how long grading our homework will take, or like, yeah, try doing it.
Well, to keep doing it's more fun than going over it.
Yeah.
It still takes more long. I remember at the beginning it took me like 3 hours to do one homework assignment. Really? Yeah.
Okay, so we are going to we are going to go and talk about essentially the potential difference that's stored when using these cells, which think of these cells as a battery. It's basically a chemical reaction, pumping electrons through a wire, very similar to what a battery does. Okay? And it has a potential difference. I know that she's probably the only one who's heard potential difference from physics. Think of it as potential energy stored up. Okay? And then used to do work in the form of electrically moving electrons or charged particles moving and doing work. Okay? Think of it that way. So we're going to figure out how big the potential difference is between your cathode and your anode, or essentially how much work it can do. Okay? The bigger the potential energy difference or potential difference that you have, the more electrical work can be done. Okay? So, we're going to consider this, we'll just kind of draw this again. Just set up the cell here. I don't know what you guys have in your notes, if you got a space or anything like
Yeah,
that.
you have to take a little space.
Okay, so there's our salt bridge. Okay, we've got one electrode. I'll say this is the cathode, which is where reduction happens. And we'll call this one the anode, which is where oxidation happens. Actually, your way has helped me a lot more than my way, so I just use your way.
I've forgotten that. When you gave the first example just now, I'd forgotten which was what that was used for. I thought that was something else, and I was like, oh, which one? Then you wrote it, I'm like, oh yeah, that one.
Yeah.
What do you mean?
Cathode,
Two
CMO.
consonants, two vowels.
Oh, yeah.
Because I use like oxidation has, I don't even remember, a D in it or something. No, I don't even remember. An O? No, they both have O's. What was it?
No.
An A?
Oh,
they both have A's.
Wasn't very good.
D. No, they both have D's. What was it?
There was
something about.
It was N. N and N, and then C and C.
Yeah.
That's what it was.
Yeah.
Really dumb.
It's not good.
Way better than his. But at least my way was better than no
Way
way.
better.
Wait, worse than his, you mean?
Way worse than his. Yes.
Way better than his.
Hey. Okay, now we need to figure out what gets. Let's just do our two half reactions. looking at this, we're going to go from a positive to a 0. That's going to get what?
Reduced.
Reduced. Okay, so I'll have a half reaction here. Where would I put the electrons here? How many of them would I put for this half reaction?
2 electrons on the left side.
So the half reaction looks like that. And it is the reduced, so we can say that's going to go over there. We'll put it in there here in a second. And then we've got our other one. Okay, we need our 2 electrons here. I'm just breaking them up into their half reactions. What do you mean by this same?
Because you break them up into the half reactions.
Well, yeah, Emily, that's already the balanced equation. That's why it's already balanced.
Yes.
That's why.
Well, sometimes I don't want to give you the balance. Remember, we had to
okay.
balance it, then we had to do the
Oh,
2
right.
separate half reactions, add. And this one's easier because there's no oxygens and the hydrogens are already balanced. So this one's kind of set up a little bit easier, but we're going to do ones where we'll have to do that process as well. But I think at this point now, we can just see if it has oxygen, add waters to balance that, add hydrogens to balance the hydrogens you just put in, and we'll do it relatively quickly, I think. Okay? So now, let me think here. So this is a metal, so I'm assuming that we can use zinc metal as the cathode there, or sorry, the anode.
In solid hydrogen.
Okay. And then we have Zn. Did you say solid hydrogen?
Yeah.
Holy food.
That would be really. Is that even possible? I mean, like.
Now, I'm guessing this came from an actual solution that broke apart. Okay, yeah, they say that this is a 1.0 molar zinc sulfate solution. So technically we have sulfate ions in here as well, but they're not going to do anything. It's not really that important information, but just in case it becomes important later. And this one, we're going to have to use a different metal. And what do you think that metal is going to be? The one we talked about, that's nerd? Yeah. Okay, so they actually have in their little picture, they basically, I think, pump in gas. Yeah. They pump in gas. And this isn't a actual, I don't know if you look in your book. Look in your book. It's like a tube.
Yeah.
Yeah, on page 827, they kind of have a blown up version of it. So we've got like this little wire there with a little platinum plate at the end for an electrode. And they pump in hydrogen gas, and as they pump in hydrogen gas, okay, it gets reduced. Okay? So we could say that this is a little platinum plate. And we have hydrogen ions in here, and H2 gas gets pumped in. Okay, great. All that stuff, we get that picture. We know electrons are going to be flowing in this direction, yada, yada, yada. Okay, what's different about what we're doing here compared to what we are going to do in this section? Okay, well, we can take a voltmeter and attach it here. And figure out the potential difference of the cell. If you hear standard state at all referring to this stuff, it's referring to anything that's dissolved being 1 molar solution and any gas that's being pumped in at a pressure of 1 atmosphere. So just in case that comes up in a homework assignment, standard state for galvanic cells are 1 molar solutions and 1 atmosphere pressure for gases.
How do you pump something out of 1
assuming it's just being done at like regular atmospheric pressure, because that's what 1 atmosphere is about, regular atmospheric pressure.
And then like pump like press the air in. Wouldn't it be more pressure than?
You might be right. I mean, you can pump something in at whatever pressure you want to set it as. They have pumps that would
But
do that.
what heat can be enough to displace the liquid and have to get bubbles down?
I don't know. I'm not sure. Okay. So what they, oh gosh, okay. Do you guys not have in your notes the two, oh you do. Okay. So you have, yeah, the two, okay, yep. 'Cause I don't have that up here on my PowerPoint. So, the accepted convention to give the potentials of the half reactions as reduction. So what I want you to do is flip the page.
Wait, is page or no?
Book.
Oh.
829. There is a chart. Okay? And that's a half reactions of a lot of really well-known common half reactions. Now, if you notice, where are the electrons situated for every one of these half reactions? Okay, it's a reactant. Okay? So all of these half reactions are set up as if they were being reduced, gaining electrons. Does that make sense? Okay? Well, we know that in all redox reactions, we have both oxidation and reduction. Okay? And what your book talks about is they had to set what they called a standard, because you're not able to figure out each individual half reaction's potential, but you can find, using a voltmeter and attaching it here, you can find the potential difference between both. And so your book talks about how they set hydrogen at 0. So what they found is they used a voltmeter and they connected it here, and they got a reading of 0.76 volts, which means the difference between the two potentials of the two half reactions is 0.76 volts. What they did is they set this half reaction to have 0 volts as a standard. Well, if this half reaction has 0 volts, this half reaction has to have the 0.76 to get the overall cell having 0.76. Then what they did is, in previous reactions, they did more reactions with this, or maybe they say they did a reaction with this, and they were able to figure out other half reaction potentials based on knowing what they got from their standard, essentially. So let me see, where did they show that? Oh, so on 827, get there. So at the top, do you see, you've got like the 3 little blue writing there, the 0.76 volts, 0 volts, and the 0.7, everybody see that?
Yeah.
Okay, so they set the hydrogen to 0, and then when they did the next one, which has zinc and copper, do you see a little bit further down? Okay. The zinc they knew is 0.76, so it should be 0.76 no matter what it reacts with. Does that make sense? And they did another situation like this, but instead of using hydrogen, they used copper. Okay? They put a voltmeter on it and found that the voltage across both of them was 1.10. So if they know the total potential is 1.10, and we have already figured out what the potential is of our zinc, 0.76, they were able to deduce what the potential of the other half reaction was. And that's where they get the 0.34. Does everybody see it? Okay, so that's how they figured out all these half reaction potentials. Okay, is they made a standard, They compared one to a standard and they continue to do comparing. Because they're unable to find a potential of just one half reaction, but they can find the potential of the whole chemical reaction. Right? The reason why knowing the half reactions potentials is really nice is if you know the half reactions potentials, you can find the total potential just by taking them and adding your two half reaction potentials. And that's where on the next page, okay, right underneath your chart, there is an equation. You're gonna, I don't know if you have this in your notes. If you don't, write it in. Your cell potential is your cathode minus your anode. Okay? Now, normally you would just add. The reason why they have minus your anode is how they have generically set up this table. This whole table has all of them in the reduction form. Does that make sense? However, we know that all redox reactions have an oxidation form. But isn't reduction and oxidation just opposites? Okay? And what happens at the anode? Oxidation. So the opposite of reduction. Or basically you're taking the opposite of its reduction value. Does that make sense? Because all of these in here are reductions. So if you flip the sign of that guy, the one that gets oxidized, you're going to get the right potential, just flip sign, which will end up working out. Okay, does that concept make sense? Why there's a negative in there based on the fact that all of these are in reduction form.
So you don't, cathode minus anode, you don't flip the sign again, you just use the number in there.
Yeah, so this number is all reduction, so when you plop it into this equation, it will flip it for you.
Got it. I just want to,
Yep.
you want to do it twice.
Yep. It should do it based on just putting these numbers in. You have to know which one's at the cathode and which one's at the anode.
Right.
But if you have those right, then yeah, just plop them into the equation. Now, there are a couple things. I want to read these two requirements. Okay, number one. It says the half reaction with the largest potential will run as written. What that means is the one that has the highest potential is the one that we're saying is getting reduced. So when it says is used as written in the book. You don't flip the sign of it. Does that make sense? Are you sure?
So when you plug it into that equation.
So, well, let's say I had a half reaction 1, and half reaction 2. This one is 2.4, and this one is 1.6. We are going to use this one as the one that gets reduced. So that's going to go in there. Okay? The smaller of the two is the one that's going to get flipped. Does that make sense? So this is going to go in here, and by the equation, it's going to take the opposite of that.
So that would be positive.
What was that?
It would be positive.
It could be whatever it is. This could be a negative, and then it would just flip to a positive.
So these values in here, like, have they already been split?
No, they're all in the reduction format. So once you find which one is the smallest number, you plug it in as the anode, and it will flip it for you.
So you don't have to do anything.
Yes. You just have to identify which number goes here and which number goes here. The bigger positive number will go here. The smaller number will always go here.
So you just put it in as it is.
And because it will flip it for you with the negative there. Yes.
If the electrons are different, can you multiply that?
No. Good question. That's what the next number 2 is going to clear up. So just be careful. What if this were negative and this were negative? Now where would they go?
Just switch to the other.
They'd be switched because technically this is the bigger number. So be careful with that. So this would go here and that would go there. Okay? I don't know if that means we're always going to get a positive voltage for E. It would make sense that they would try to set it up so that you always get a positive E.
It would make sense to do negative voltage.
What?
Do negative
It
voltage.
would always be
makes sense.
positive. So
for the whole.
I think so.
system.
I mean, you can get a negative potential difference, but it's really just sign convention problem. It would be direction of flow instead of,
Right.
the magnitude would still be the same.
Right.
Anyway, okay. Shoot. So number 2, it says, since the number of electrons, since the number of electrons lost must equal the number gained, the half reactions must be multiplied by integers as necessary to achieve a balanced chemical equation, which is what we did last week, right? The value for E is not changed when a half reaction is multiplied by an integer. Okay? There was something that said as to why, I don't remember.
It's right.
It
Next one.
says, since a standard reduction potential is an intensive property, it does not depend on how many times the reaction occurs, the potential is not applied. It's due to the potential energy difference between the beginning and the ending. It doesn't matter how many times you react. Okay? Alright, so let's do a problem here. Probably have time for one. We'll finish the rest tomorrow. So let's do.
Line notation.
We'll do that. This one, I think, is the next one on your homework. Is that right? So we could set up a visual diagram and do the pictures like we just have done. It's not super necessary. Okay. What I would do is I would identify both half reactions. Okay, and since there's no oxygen or hydrogen, we don't have to do anything crazy. So we have Fe3 plus goes to Fe2 plus, so that would be the one that gets what? Okay. Okay, the other one. Now, let's go just quickly figure out what the voltage or potential difference of these two half reactions are. So look in your book and see if you guys find those for me.
It's 0.16 with this CU.
It is? It's not what my thing is showing. Is there two of them?
There's a CU plus a CU, which is 0.02. CU.
Oh, we want the Cu2 plus 1.
So that's
0.34.
Oh, I just hit the plus of that.
It should be in the top right. So be careful. Make sure it matches perfectly, because there's a variety of ways of, we can get different ions. Does everyone see the 0.34?
Yeah.
Okay, so this is going to have a, I don't know how to write this.
There was CU2 plus.
Better keep the signs correct. And how about the other one? Not in there?
It's 0.77.
Yeah, 0.77. It is near the bottom on the left side, like the big one up. Okay? Now, we do know that this lost 2 and this only gained 1. So technically, if we were doing a balancing thing, we would have to multiply this by 2. Okay, now remember, that doesn't affect the potential difference at all. So it's not necessarily needed unless they ask you to do a balanced chemical equation. Because we could take now these two half reactions, we can go like that, and it's technically balanced so that all the electrons gained and received are the same, or sorry, lost and received are the same. Okay? But really the end goal of this here is to find the potential difference of the cell. Okay? Which one is the one that we're going to say is going to stay as is, or is going to be the one that's reduced? The 0.77. So we're going to say that is the one that's going to stay as the cathode, or on the cathode. Okay, minus 0.34. This is happening at the anode. So our particular cell here, if we were to put a voltmeter up on the wire and figure out the potential difference across the cell, it should be 0.43. That would be my potential difference for this particular cell. Okay? We will finish this lesson tomorrow and then move on to 18.4.